All right, so let's get this matter out of the way. Yes, matrices and vectors are very much the same thing. In fact, a matrix can be viewed as a vector of vectors. And that can be done in two ways. I can either see a matrix as a vertical vector of rows. So in other words, I can think of the matrix A as a vector whose components are actually vectors. So each of those vectors being a row of what I have in mind as my matrix. Or I can see a matrix as a horizontal vector of columns. So I can think of my A as a vector where each of the components is in fact one column of the original matrix. Okay? So notice there's a lot of interplay between vectors and matrices, but it doesn't end here. Vectors can be seen as matrices, right? You can think of any row or horizontal vector as a one row by n column matrix, right? So I could write a vector as v11, v12 up to v1n. Of course, the 1 being the first number 1, being the same in all of the components, we don't bother to write it down, but that's what it is. And similarly, any column or vertical vector, remember we can write vectors either horizontally or vertically, can be thought of as an m row by one column matrix. So I could write a vector in that way, but this time the second index is really useless because it's always the same. So normally we don't do it. But again, we can view matrices as vectors, vectors as matrices. They're really the same object, just in different contexts. And that is another reason, once again, why I chose to use a square bracket notation for vectors, because that's really the same notation as for matrices, and so we keep consistent with that. Okay. Now, let's start with a little bit more terminology for any whole number n. If I look at an n by n matrix, same number of rows and columns, for obvious reason we're going to call it a square matrix, right? It's going to have the same number of rows and columns. Okay. For instance, there are some square matrices that will play a very important role. So let's make their acquaintance. Here are our special square matrices. First of all, the zero matrix. Absolutely pathetic, isn't it? Obviously, the zero matrix is the one where every entry is just zero. Okay, so it doesn't matter which row or column we're in, the zero matrix is showing a zero in there. Now, because we can construct the zero matrices of any dimension, sometimes we can, if it's important, we can add the little subscript that tells us a zero matrix of what dimension or what size. However, be careful because those two subscripts can get confused with the entry. As long as the context is clear and we know if we're talking about the whole matrix of dimension mn or whether we're talking about the entry in position mn, well, then we're okay. But otherwise, you may want to be careful with these notations. Next very important matrix we're going to meet is the so-called identity matrix. And again, there is one identity matrix for each size. Remember, these are all square matrices. So sometimes we're going to add the little subscript n to denote identity matrix of what dimension. But if we don't need to, we better not put that in, just not to confuse and not to make the notation heavier than it is already. Okay. So how is the identity matrix defined? Also very simple, not as simple as the zero matrix, but almost. Okay. So the elements or the entries of this matrix are going to be 1 if they're in a position where I is equal to j. So in position 1 1, 2 2, 3 3, and so on. Otherwise, it's going to be 0. So an identity matrix looks like this. It's going to have 1 in what we're soon going to call the diagonal of the matrix and 0 everywhere else. Again, very simple matrix, but we're going to see very soon that this has very, very important properties. Now let's have a look at some special types of matrices, in fact, special types of square matrices. First of all, we're going to look at diagonal matrices. These, as the name indicates, are matrices that only have entries along the diagonal. Well, that's not quite right. A matrix always has to have entries in each position. Okay, but what I mean is that we're going to have some number if we are on the diagonal, if the subscript I and j are the same. Otherwise, it's going to be 0. So it's pretty much like the identity that we just saw, except that we're not going to require diagonal entries to be 1s. In fact, they can be whatever they want. Okay. So on the diagonal, we're going to have any numbers we want, including 0 if we want. And outside of the diagonal, we must have zeros. So both the zero matrix and the identity matrix are diagonal matrices. By the way, again, let's get another elephant out of the room. The set of all those elements, which you can actually think of as a vector because it is an ordered set of elements along in those particular positions of a square matrix, is called the diagonal. Obviously, I've mentioned that already a few times, but just to get the thing perfectly clear. Another type of matrices are so-called symmetric matrices. Again, they have to be square matrices. What is a symmetric matrix? It's a matrix where any element in position ij is going to be exactly equal to the element in position ji. In other words, the element which is opposite to it in the matrix with respect to the diagonal. So a symmetric matrix will look like this. It will have whatever you want on the top left, and then as soon as we get a number in the next position, we must have the same number at the opposite side of the diagonal. Again, on the diagonal we can put whatever we want, but as soon as we're looking at elements on the opposite side of the diagonal, they have to be the same. So for instance, again, this element here is equal to this element here, because this first element is the element 2, 3, and this element is the element in position 3, 2. So they have to be the same. So that's the whole idea of a symmetric matrix. Some other types of matrices, still square and still very similar to the ones we've seen so far, just with more fancy names. An upper triangular matrix is a matrix which is defined by these conditions. We can put any number we want if the first index, the row number, is less than or equal to the column number, and 0 otherwise. So what does it turn out to give us? It turns out to give us a matrix that looks like this. Anything below the diagonal has to be 0. Does that look familiar? That's a row echelon form, doesn't it? But it's a particular kind of row echelon form. Okay. But anything on the diagonal or above can be a number. That's why it's called an upper triangular. And anything below the diagonal has to be 0. Once we have this smart idea, we can define a lower triangular matrix by reversing the two conditions, by requiring that anything above the diagonal is going to be equal to 0, and anything on or below the diagonal can be any number we want. So it's going to be a matrix that was going to look somewhat like this. So again, those A, B, C's and so on can be anything we want, but the numbers above the diagonal have to be zeros.